Hello viewers, my name is Dr. Kishen Ajay Kumar, Associate Professor in the Department of ECE from Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today we are going to discuss about the topic range in space wave propagation, the duct propagation and also the fading. So today's topic is range in space wave propagation and duct propagation and fading. So this is the topics which belong to the course Antennas, Waves and Propagation. Let us start our session. So in space wave propagation, there is a transmitting antenna and the receiving antenna. Whenever a signal travels directly from the transmitting antenna to the receiving antenna without any reflection, a path is established. That path we call it as a line of sight. So the line of sight is that the distance between the transmitter and the receiver, in which if a direct ray passes from transmitter to the receiver without being intercepted in the Earth's surface. So you can see here, there is no any reflection or any obstacle in between the transmitting antenna and the receiving antenna. So here there is a direct path is established between the transmitting antenna and the receiving antenna. So here a ray is passing from the transmitter to the receiver without being interception in the Earth's surface. So in the line of sight communication, the wave travels a minimum distance of sight, which means it travels to the distance up to which a naked eye can see. So we need to employ an amplifier from transmitter here to amplify the signal and transmit again. So here whenever we are going to transmit a signal from longer distances from transmitting antenna to receiving antenna, an amplifier is required between the transmitting antenna and the receiving antenna to establish a line of sight communication. To establish a line of sight communication, a wave travels to the distance up to which a naked eye can see. When the distance increases between the transmitting antenna and the receiving antenna, then an amplifier is required to amplify the signal and transmit it again to the receiving section. Now let us calculate the range of space wave propagation. Let us calculate the range of space wave propagation, assuming Earth as curved Earth. So assuming Earth as curved Earth, we shall calculate the range. Range means the distance between the transmitting antenna and receiving antenna. So Hilbert's propagation is possible in space wave propagation above 30 MHz of frequency. In space wave propagation, we transmit the signals above 30 MHz of frequencies only. Let us see the figure here. There is a radius of the curvature R dash. R represents the actual radius of the Earth, and R dash represents the radius when the Earth is curved. So R dash is equal to, we know that 4 by 3 into R. So we need to remember that R dash is equal to 4 by 3 into R. So here R represents capital R represents the actual radius of the Earth, and R dash represents the radius when the Earth is curved surface, when the signal is propagating over the curved surface of the Earth. So there is a difference of 4 by 3 between the actual radius and the curved surface radius. So let us assume here there is a curved surface of the Earth. Here this is the curved surface as shown in the figure. HT represents. Assume that HT represents the height of the transmitting antenna, and HR represents the height of the receiving antenna. HR represents that this is the height from here to here. This is HR represents the height of the receiving antenna, and also the HT here from here to here. HT represents the height of the transmitting antenna. And let us assume that the total distance a ray is traveling from the transmitting antenna to receiving antenna is capital D. So here D max represents the maximum distance a ray is propagating between the transmitting antenna to the receiving antenna. Assume that the ray has been divided into two parts, D1 and D2. Assume that the ray is touching the surface of the Earth. Assume that the ray is touching the surface of the Earth midway between the transmitting antenna and the receiving antenna. Assume that the ray path is touching the surface of the Earth, surface of the curved Earth exactly at the midway between the transmitting antenna and the receiving antenna. So let us assume the D1 as the distance from the transmitting antenna to the this point, and D2 is the distance from the receiving antenna to the midpoint of transmitting antenna and the receiving antenna. So here from the figure we can say that the total distance, that is a ray is traveling from transmitting antenna to receiving antenna, is defined as a d, which we call it as a range. So d is nothing but the range of a ray path which is traveling from the transmitting antenna to the receiving antenna. From the figure you can say here d is equal to d1 plus d2. From the figure we can say that the total distance traveling a ray is given by d1 plus d2. Now let us simplify the value of d separately by calculating the values of d1 and d2. By calculating the values of d1 and d2, let us find out the values of d1 and d2 separately. So from the figure, if we assume here as O, this is A and this is B and this is C. Let us assume this as O, A, B and C. So from this O, A, B, C, let us take the triangle O, A, B. If we take the triangle O, A, B, so if we apply the Pythagoras theorem for this triangle O, A, B, so we can get that d1 square is equal to, from the Pythagoras theorem, we can get OB square plus OA square. So d1 square is equal to OB square plus OA square. So where OB square is nothing but R dash square plus OA square is nothing but, here you can see here ABC, let us assume this as D and this as E here. So OA is nothing but, OA can be written as OD, from the figure, OD plus AD whole square. So we can write as OA whole square is equal to OD plus AD whole square. So from this you can write as R dash square plus, what is OD here? OD is nothing but R dash plus R dash, here AD is nothing but, it is HT. It is HT whole square here. So here we are getting d1 square as R dash square plus R dash plus HT whole square. Now let us simplify this d1 square value again. So d1 square is equal to, you will get R1 dash square plus R1 dash square plus R dash square, R dash square plus 2R dash HT plus 2R dash. So A plus B whole square is equal to A square plus B square. You will get HT dash whole square, HT whole square. So you will get here R dash square plus R dash plus HT whole square means R dash whole square A square plus B square HT whole square plus 2AB, 2 into R dash into HT. So if you simplify this, you will get 2 R dash square plus 2 R dash HT plus HT whole square plus HT whole square. So we know that R dash, that is the radius. The radius is that is approximately 6370 kilometers. Practically, the height of the receiving antenna is around 200 meters. So when compared to the radius, the height of the transmitting antenna and the height of the receiving antenna are very small. So when compared to the radius of the Earth, the actual radius of the Earth is 6370 kilometers, but the height is of the transmitting antenna is 200 meters. So as the radius is very high, you can here ignore. We can ignore this value HT square. So HT square can be ignored here. We ignore this HT square, you will get 2 into 2 R dash into, one second. So here you can see here from the d1 square is equal to R dash plus HT whole square minus R dash square, the first equation. So d1 square is equal to R dash whole square plus 2R dash HT plus HT whole square minus R dash square. So from this equation, you can write here, sorry. So here you can read from the triangle OA and B, you can write here D1 square plus R dash square is equal to HT plus R dash whole square. So from the triangle OAB, we can write this as D1 square plus R dash square is equal to HT plus R dash whole square. So here we simplify D1 square plus R dash square is equal to HT square plus R dash square plus 2 R dash into HT. So R dash square get cancelled. You can write D1 square is equal to HT square plus 2 R dash HT. So I told you that R is far greater than HT. The radius that is very large in kilometers and the height of the transmission is in meters. So as R is far greater than HT, we can ignore this HT square value. We'll get D1 square is equal to 2 R dash HT. D1 square is equal to 2 R dash HT. Similarly, for triangle OEB, if we take the triangle OEB, you will get D2 square is equal to 2 R dash into HR. So D1 square is equal to 2 R dash into HT and D2 square is equal to 2 R dash into HR. From this value, you will get the value of D1. D1 is equal to root of 2 R dash into HT. At the same time, what you will get D2? D2 is equal to root of 2 R dash into HR. So here, if you simplify, you will get the value of D1 as root of 2 R dash into HT. And similarly, you will get the value of D2 as root of 2 R dash into HR. So, according to the range definition, D is equal to D1 plus D2. According to the range definition, D is equal to D1 plus D2. So, let us substitute these two values, equation 6 and equation 5. Equation 4 and equation 6, we shall substitute in this equation D max. If you substitute, you will get root of 2 R dash HT plus root of 2 R dash HR, where R dash is the radius of the curved surface of the earth, or the effective radius of the earth. So the effective radius of the earth is given by R dash is equal to 4 by 3 into R. So the R dash represents the effective radius of the earth. See here, we can see here, there is a relationship between the effective radius of the earth and actual radius of the earth by where R dash is equal to 4 by 3 into R. Now let us substitute the value of R dash in the above equation, that is in this equation. So we shall substitute here R dash is equal to 4 by 3 into R. We shall substitute here R dash is equal to 4 by 3 into R. So if we substitute 4 by 3 into R, we will get 8 by 3 R into HT plus root of 8 by 3 into R HR. So root of 8 by 3 into R HT plus root of 8 by 3 into R HR. So for the radius of the, we know that 6370 kilometers. So let us substitute this 6370 in the value of R. Let us substitute this 6370 kilometers in the value of R. So if we simplify here, by substituting, we will get 8 by 3 into 6370 into 10 power 3 into HT plus the same thing. 8 by 3 into 6070 into 10 power 3 into HR. So if we substitute these two values and further simplify, so you will get a value as D max equal to root of 8 by 3 into 6.37 into HT plus root of 8 by 3 into 6.37 into HR. So here we have converted into 10 power 3 as outside here. We are taking this 10 power 3 outside here. So here we are measuring in terms of kilometers here. 6070 kilometers here. R is, we can also write this as a 6.3 into 10 power 6 here. 6370 kilometers can be written as a 6.37 into 10 power 6. So the same thing we have written here, 6.37 10 power 6. So 10 power 6, 10 power 6 root is given by 10 power 3 here under square root. So 10 power 3 is taken as a common. And if we simplify these two equations, you will get approximately 4.12 into root of ht plus root of hr. Here we are having one 10 power 3. So 10 power 3 represent kilometers. 10 power 3 represents 1000 meters or in kilometers. So d max is represented only in kilometers only. The range of a path in space-wave propagation is represented in only the kilometers units only. So the line of distance is expressed in kilometers, which depends upon the height of the transmitting antenna and the height of the receiving antenna. So here, due to the curvature of the Earth, the line of sight transmission is limited to the horizon. So due to the curvature of the Earth, the line of sight transmission is limited to the horizon. The locus of points and distance at which direct rays become tangential to the surface is known as radio horizon. So as we have seen here, there is a curved surface here. The locus of all the points which is tangential. Tangential means which touch the curved surface of the Earth. This line we call it as a tangential line to the surface. This path we call it as a tangential path to the curved surface. Hence, this path we call it as radio horizon. This path we call it as a radio horizon. So a radio horizon is observed circular on a spherical surface. The maximum distance between two antennas along the surface of the Earth, such that the ray from the transmitter just touches the surface of the Earth, is known as optical horizon. A maximum distance between two antennas. The maximum distance between two antennas along the surface of the Earth, such that the ray from the transmitter just touches the surface of the Earth, is called as optical horizon. Here, the effect of bending of the radio wave in the atmosphere can be taken into account by taking a greater radius to the Earth. That is, it actually has. And then radio wave is taken to travel in the straight path. So, for standard atmospheric condition, the effective radius of the Earth is given by r dash is equal to 4 by 3 into r. The radius of the Earth for standard atmospheric conditions is represented as r dash is equal to 4 by 3 into r. So, the range is given by, we have seen the derivation here. The range is given by 4.12 into root of ht plus root of hr. 4.12 into root of ht plus root of hr. Now let us come to another topic. The next topic, that is duct propagation. Let us come to the next topic, which is known as duct propagation. Here, the radio wave propagation technique that allows the transmission of ultra high frequency and very high frequency electromagnetic waves through the region near a tropospheric layer of the atmosphere, which is known as a duct propagation. So here, in the atmosphere, we are having two types of atmosphere. One is a standard atmosphere, the other one is a non-standard atmosphere. One is standard atmosphere and the non-standard atmosphere. So both these atmospheres depends upon the refractive index of the layer. Both these atmospheres, either it may be standard or non-standard atmospheres, depends upon the refractive index of the layer. Here in standard atmosphere, it is a condition where simply a refractive index is enough. Simply a refractive index is enough for establishing a path between the transmitting antenna and the receiving antenna. Here, generally, the standard atmosphere, for standard atmosphere, the value of n is given by mu plus h by r. Mu plus h by r. So, for standard atmosphere, the refractive index or the refractive index given by the parameter mu plus h by r. So it depends upon the height and the radius of the Earth. It depends upon the height of the transmitting antenna and also the radius of the Earth. But for non-standard conditions, we need to modify this equation. Substitute adding both sides minus 1, we'll get n minus 1 is equal to mu plus h by r minus 1. Mu plus h by r minus 1. And this n minus 1, we call it as capital M, which is known as the modified refractive index. It is given by mu minus 1 plus h by r. modified refractant is given by m is equal to mu minus 1 plus h by r. So for standard atmosphere, we can write simply the refractive index as mu plus h by r, and the modified refractive index is for non-standard atmosphere, it is given as m is equal to mu minus 1 plus h by r, mu minus 1 by h plus r. So duct propagation is generally possible in the tropospheric layer, that is over the surface of the earth around 16 kilometers, over the surface of the earth above 16 kilometers. Basically in duct propagation, and despite being reflected from the ionosphere or gliding over the surface of the earth, the waves propagate from an end to end by undergoing successive refraction from the troposphere. So as we know that in the atmosphere, there are different layers. There are different layers in the atmosphere, D layer and E layer, F1 layer and F2 layer. As when we send a signal into the atmosphere, this wave will penetrate into any of these layers. This wave will penetrate any of these layers. So at each layer, refraction is going to take place. At each layer, refraction is going to take place. That means successive refraction from the troposphere is possible in the space wave propagation. So to explain about the duct propagation, we need to have a knowledge of M cos. We need to have a minimum knowledge of M cos. So what are known as M cos? So here we have seen that M is equal to, as if this is not mu M, this is capital M. So M is equal to mu minus 1 plus h by r into 10 power 6. So this is the modified refractive index. And D, if we vary this modified refractive index with respect to height, we call it as gradient. dm by dh. dm by dh is equal to, it is known as the gradient, or we can also call it as a slope. Here, the value of dm by dh depends upon the atmospheric conditions. So dm by dh may be positive, or maybe it may be negative. So it depends upon the slope of the M curves, depends upon the atmospheric conditions. So if we draw the graph between the modified refractive index, those curves we call it as M curves. If we draw a curve between M and H, we call those as M curves. We call those curves as M curves. That means, suppose if this is M and this is H. So if we draw a curve by varying modified refractive index with respect to H, the curves which we get here, we call it as, these are known as M curves. So the refractive index of the A here varies as the signal is propagating from one layer to the other layer. So the refractive index of the air is defined as the root of the dielectric constant that is denoted by mu. So for studying of radio wave propagation, the actual refractive index is expressed in terms of a modified refractive index, which is given by m is equal to mu minus 1 plus h by r. So here capital M is equal to mu minus 1 plus h by r. So duct propagation is also sometimes referred to as super refraction. It allows the propagation of signals beyond the horizon. So in duct propagation, along with the M curves, there is a layer known as inversion layer. So we know that, let us assume here this as a transmitting antenna, and here let us divide this into three zones here. This is the first zone, this is the second zone, and this is the third zone. So as the height increases, we know that as the height is increased, there will be a large amount of heat in the atmosphere. After 16 kilometers, as the height is increased, the air will be very cool. So from the surface of the earth, as the height is increased, air will be very warm, and after 16 kilometers, there is a change of the atmospheric conditions. There will be cool air will be transmitting in the second zone. See here there is a warm air, here there is a cool air. And further, after 10 kilometers from the second layer, again there is a layer which becomes very warm, which is a warm layer. So here, if we draw the curve, that is dm by dh. So in the warm layer, it is positive here. If we draw a curve, representing dm by dh, modified refractive index with respect to the height, that is the slope. So here in warm, in the first layer, this dm by dh will be like the path will be, the ray path will be like this. But in the second layer, the air is very cold. That means the wave is traveling from rarer medium to the denser medium. Here the dm by dh will be negative. Dm by dh will be exactly opposite to the layer 1. So these are known as the standard condition, standard atmosphere, and this is the non-standard atmosphere. So non-standard atmosphere is one where inversion layer exists. Non-standard atmosphere is one where the inversion layer exists. That means exactly opposite to the standard atmosphere, the ray path will be traveling. The ray path, electromagnetic rays will be traveling exactly opposite to the standard atmosphere. Again, you can see here in the third layer. Again, you can see in the third layer, the ray path is again transmitting according to the standard atmospheric conditions. According to the standard atmospheric conditions. So here you can see here the dm by dh value varies with respect to the height of the transmitting antenna. So here it is positive, here it is negative, and here it is positive. Here it is positive. So here like this, the inversion layer exists in the duct propagation. Like this, the inversion layer exists in the duct propagation. Here, whenever the wave is transmitted, whenever the ray is transmitted, the ray is traveling into the free space along many layers. So here, layer 1, there is layer 1, the air is warm, and the layer 2, it is cool. So in the cool area, the air will be very denser. Duct formation takes place in the second layer, where the air is very cold. So here the refraction takes place. You can see here, this is one layer and this is another layer. Like this, 1, 2, 3, and 4. You can see here, as the ray is propagating here, this is the duct formation takes place here. That means the path is traveling from a rarer medium to the denser medium. The ray is traveling from 1 to 2. There is a rarer medium to the denser medium. Here duct propagation is happening here. A duct is formed in the second layer. And here the humidity will be very less. And here refraction is going to take place from 1 to 2. When the ray is propagating from 1 to 2, here the refraction takes place here. And after it strikes the surface of the third layer, and reflection takes place here. Again, when the ray travels from the cool area to the warm, that is the third layer. The third layer, it is a rarer medium. So again, refraction is going to take place. So like this, multiple reflections takes place when electromagnetic wave is traveling among different layers in the atmosphere. Hence, the duct propagation is sometimes referred to as super refraction. So here the ray is traveling from 1 to 2. One refraction is taking place from rarer medium to denser medium. And from 2 to 3, another refraction is going to take place. Why? Because the ray is again traveling from the denser medium to the rarer medium. From the cool area to the warm area. Hence, multiple types of refraction is going to take place. Hence, we call the name is given as a super refraction. That is, the duct propagation is sometimes referred to as super refraction. So it allows the propagation of the signals beyond the horizon. This means, unlike surface wave propagation, it permits the signal transmission without assuring the need for having a line of sight distance between two antennas. So due to the duct propagation, the wave is traveling either in a single path or multi-paths. So if a wave is traveling in a single path, we call it as a single hop propagation. If a ray is traveling in multiple paths, we call it as a multi-hop propagation. You can see here, if you take a transmitting antenna here, and here there is a receiving antenna, here there are two layers. Here, if a wave is directly, here there is the rarer medium, and this is the denser medium. When the wave is traveling, here the refraction takes place, 1 and 2. and the wave is directly coming to the receiving antenna. Here the transmitting antenna. So I can see in the figure, you can see in the figure, there is a single path or single refraction is going to take place between 1 and 2, and after refraction, the wave is going to reflect back to receiving antenna with only one path. So this we call it as a single half propagation, as there is only one path. As there is only one path, we can call it as a single half propagation. So single half propagation is possible in the duct propagation. We can also have a multi-half propagation as the distance increases, as the distance between the transmitting antenna and the receiving antenna is more, and as the ray is propagated around a distance of 16 kilometers above in the space of propagation, as the wave is traveling here, the ray is going to travel here. There is one refraction is going to take place, and again it's going to strike the surface of the earth, and again it's going to reach to another point here. Here again refraction is going to take place, and again it is getting back to the ground, and from the ground is going to reach to the receiving point. So here there are 1, 2, 3 and 4. Here there are 4 paths. There is the electromagnetic wave signal transmitted by the antenna from the transmitting section. The wave is traveling in 4 different paths due to the refraction from the duct propagation. So this we call it as a multi-half propagation. As the wave is traveling, having different paths from transmitting antenna to the receiving antenna, we call it as the name is given as multi-half propagation. And half means path. Half is, you can simply call it as a path. So due to high frequency, the signals in the troposphere require an obstruction-free path as wavelengths of such high-frequency signals are short. So this mode of propagation limits the range for signal transmission. So for UHF and VHF signal transmission to an even greater distance, the duct present in the tropospheric atmosphere is utilized. So all the ultra-high frequency and very high frequency signal transmission, though duct is present, it is effectively utilized in the tropospheric region. So due to the presence of duct, we can exhibit the single half propagation, multi-half propagation. We can also transmit the antenna into this layer where reflection and reflection takes place towards the receiving antenna. So this duct acts as a channel to guide the high frequency wave to the other end by successive refraction. Hence the name is given as a super refraction. Hence the name is given by super refraction. As the wave is traveling multiple times, here we can have one refraction here. Again another refraction is going to happen here. So another refraction is going to happen here. So like this, multiple refractions are going to happen in the different paths in the atmosphere, in different paths. So this is the warm air, and here there is a duct is present. So the ray is traveling from 1 to 2, 2 to 3 and 3 to 4 where refraction takes place and also reflection takes place towards the receiving antenna. So troposphere is generally extended up to a range of 15 kilometers from the surface of the earth. The tropospheric layer is nothing but it is at a distance of 16 kilometers from the surface of the earth. So the duct propagation takes place nearly above 50 meters above the tropospheric region. Above 50 meters, duct propagation takes place nearly about 50 meters above the troposphere. So 50 meters is the range where duct propagation takes place above 15 kilometers on the surface of the earth. Thus, we can say that duct propagation occurs in the tropopause or stratosphere. In the tropospheric region, we call it as simply as a tropopause. We can also call it as a stratosphere region also. So above the troposphere, there is another layer which is known as stratosphere. So that propagation takes place in the stratosphere. Duct propagation occurs when a duct is formed in the lower layer of the atmosphere. So duct is nothing but the region of cool air. Duct is nothing but the region of cool air present between the layers of the warm air. So the formation of the duct is the outcome of the temperature inversion. The formation of the duct is the outcome of the temperature inversion. So here the temperature inversion is the concept where as the distance is increased 16 kilometers, there is warm air, and after 16 kilometers there is cool air. That means the heat is the temperature will be increasing here. As the height is increased, the temperature is increased. Here, the temperature is decreased. And after again another region, the temperature will be increasing. The temperature is increased. So where the temperature is decreasing, the duct is formed in that layer. So the formation of the duct is the outcome of a temperature inversion. We also call it as temperature inversion or inversion layer. Or inversion layer. We can also call it as inversion layer. So we know that in a standard atmosphere, the temperature shows reduction with height. The temperature shows with reduction with respect to height. This means that in the upward movement in the atmosphere, the dielectric constant must decrease uniformly. So this means that the upward movement as the signal is propagating into the atmosphere, the dielectric constant must decrease uniformly. So this will lead to have unity dielectric constant in the region of 0 air density. So this will lead to the unity dielectric constant in the region of 0 air density. Practically, the standard atmospheric condition shows rare existence. So practically, the atmosphere is never standard. Why? Because the dielectric constant and the refractive index in the atmosphere will be continuously changing. So always, practically, we consider a non-standard atmosphere where the refractive index varies. Practically, a standard atmospheric condition is not possible. Is not possible. The reason behind this is that air is of turbulent nature. Also, there exist different layers of air. So there exist different layers of air. So in the standard atmosphere, is one where temperature reduces with respect to height. Temperature reduces with respect to the height. So initially, as the height is increased, temperature increases, and if you increase further the height, the temperature will be in a reverse direction. That is, the temperature decreases with respect to the height. So this means that the upward movement in the atmosphere, the dielectric constant must decrease uniformly. So here, practically, standard atmospheric conditions never exist. So we are going to consider only the non-standard atmosphere in different layers of air, in different layers of atmosphere. So these multiple layers of air contain different water vapor content, thus different temperatures. So the property of significantly having a decrease in temperature with height gets failed to be achieved. So this leads to the development of an unusual situation in the atmosphere where a layer of warm air exists above the cool air. So as we have discussed just now, there are multiple layers in the atmosphere with different water vapor contents in the temperature. With different temperature, different molecules are present, different water vapor contents are present with different temperatures in the atmosphere. Different ionized gases are present in the atmosphere. So the property of having a decrease in temperature with height gets failed to be achieved. So there is an unusual situation in the atmosphere where a layer of warm air exists above the cool air. So this is known as a temperature inversion or inversion layer, and this gives rise to the phenomenon of super refraction in the atmosphere. So and this gives to the phenomenon of super refraction in the atmosphere. So you can see here the duct propagation here. Here this atmospheric duct is formed here. This is the curved surface of the earth here. And there is multiple refraction. Refraction is going to take place. One reflection, this is another reflection, and this is another reflection. So this we call it as multi-half propagation. So from the transmitting antenna, from the duct, here there is a duct here. From the duct, the refraction is going to take place. After refraction, the signal is getting reflected to the ground, and from the ground again it is going to touch the surface of the duct, and again it is going to reach to the ground here, and from the ground here again it is going to reach to the receiving antenna. So here the duct is responsible for happening of multiple reflections and refractions in the atmospheric layer. So trapped wave propagating a series of hops. So here the electromagnetic waves are trapped between the duct and the ground. So here this is known as a duct layer. So between the duct layer and the surface of the earth, all the electromagnetics are trapped in series of hops. So this series of hops of paths, we call it as multi-hop propagation. The concept of wave trapping can be considered as a phenomenon similar to waveguide. So, but the main difference between the waveguide and the duct propagation is that in waveguide, all the modes are confined within the guide only. But in case of duct propagation, part of energy within the duct may be escaped to the free space as shown in the figure. So here we can observe here when we are going to transmit the signal from the transmitting antenna, some of the energy will be reflected towards the receiver. As the wave is going like this, the waves will be reflected towards the receiving antenna. But there is a chance that some energy will be leaked from the duct towards the next layer. That means there is a possibility that some amount of energy is going to escape into the free space. So in case of duct propagation, some portion of energy is trying to escape into the free space as shown in the figure. So, but in waveguide, you can see here in the waveguide, all the electromagnetic energy is confined within the guide only. So there is no any loss of energy in the waveguide. There is a little loss of energy in the duct propagation also. There is some energy leakage in the duct propagation also. So the refractive index of the air is modified, defined as the root of dielectric constant. So it is given by m is equal to mu minus 1 plus h by r into 10 power 6. And this is known as a standard atmosphere. In standard atmosphere is one where the variation of a modified refractive index with respect to height is given as 0.1181 meter per meter. So the refractive index, modified refractive index is equal to 0.1181 per meter for standard atmosphere. So the modified refractive index expression is mu minus 1 plus h by r. So here we can observe here a duct layer is found. There is a temperature inversion is going to take place. Here this is an inversion layer where exactly opposite it is happening here in the duct. This is a non-standard atmosphere and this is the standard atmosphere. You can also see here there is an elevated duct here. Here the electromagnetic rays or refraction is going to take place. The waves are propagating from one layer to the other layer, from one layer to the other layer. Here also inversion is, the temperature inversion is happening in this elevated duct. So simple surface duct, it is ground based, it will like this. So the path in the elevated duct will be like this. So inversion layer is happening due to the decrease of temperature with respect to the height of the transmitting antenna. There is a limit on the wavelength of signal of maximum value to be trapped in the duct. So it is a maximum wavelength for which the duct propagation holds good. So if the wavelength of t, the signal exceeds the value max, then duct effect vanishes almost completely. So the value of lambda max must be given by 2.5 HD into root of del mu m into 10 power minus 6. So this is the maximum value where the signals that has been sent from the transmitting antenna will be trapped in the duct. So lambda max must be equal to 2.5 HD. It is the maximum wavelength for the duct propagation holds good. So duct propagation is possible only under this frequency only, where the wavelength is given by 2.5 HD into root of del mu m into 10 power minus 6. So beyond this value, the electromagnetic rays will try to escape into the free space. So beyond the lambda max value, the electromagnetic rays that we are propagating, those will be vanished completely into the free space. Those will not be reflected. Those will not be reflected above the lambda max value. So the maximum wavelength in centimeters given in the table here, 10 duct height must be 500 for a maximum wavelength of 1 centimeter. The duct height is 500 centimeters. For a wavelength value of 10 is equal to 2300 HD in centimeters. For the maximum wavelength of 100 centimeters, the duct height is 10,700 in centimeters. And the maximum wavelength for 1000 centimeters is given by 50,000 in centimeters. The duct height is 50,000 in centimeters. So here, with this we close the session today. We have discussed about the line of sight today. We have discussed about the range of space wave propagation, which is given as 4.2 into 4.12 into root of HT plus root HR. And we have also seen the duct propagation. So for references, you can refer these textbooks, the KD Prasad and V.A. Bakshi. Also, you can prefer Cross. You can also prefer John D. Cross and Balanis. So these are the standard textbooks. You can follow these topics in these textbooks. Let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.